start again. Okay. So before I continue, I will just talk a little bit about the example I started with, which was the translation.
I should probably draw this side.
So in this example, let's say you have a vector only that is for the Avogadro 2D. Now, I would like to just move it 10 units, or actually it's another vector, it's 10, 10, 10, 1, but instead of drawing that, it's a bit difficult on the screen. So let's say it's 10, and then 10, like that. And then I just move it 10 more units to the right, so you end up as 20 and 10. And then of course it stays the same in the z direction as well. Like you do with this particular example. So you have a vector 10, 10, 10, and then you add another 10 units, put it in to the top there, and you will just move it, shift it along the x-axis. And that you do by this GLM code here. GLM translates, then you specify it's a 4x4 matrix, and you basically set X, Y, and C translation. Then we go to scaling. It's more or less very the same thing, except that now you don't have the outmost column, you have a diagonal matrix, and you scale X, Y, C. So it's like what I just showed with this object here. If it's like +1 here, +1 here, and I will map this one to, I should draw over there because then the camera can see. So if you have this one, +1, +1, and then +1, you have a cube standing out here. But I should improve my drawings just before I try that. Then what I will get out is basically X minus X, then minus Y, and plus Y here. Of course, X and Y can also be that shrink the whole thing. So I basically map here by this scaling operation. To do that in OpenGL, it's basically to that was that. The example here, basically, you scale by a factor of 2. So, and I can be more specific, and I can say that these numbers are all 2, right? So from -2 to +2, from 2 to -2, right? So you just double the size of the whole thing, and you keep its original shape. And you can do this quite simply in using GLM library as well. So you say GLM scale, and then the scaling in X direction, scaling in Y direction, and the scaling in Z direction. It's a very simple way of coding this using the GLM library. Right, so to rotations. And before we talk about that, we need to understand why the rotation matrix looks the way it does. And I would just like to recollect the definitions of sine and cosine, because that basically tells you why. So if you have a triangle here with sides A, B, C, and then you have to figure out the sine of this theta angle, that's basically the face B divided by the hypotenuse. So B divided by C. And similarly, cosine is defined as A divided by C. Just to remind your basic math things. Now, if you have a unit vector, which means a vector that's bound at the origin and ends up and always has length 1, it will always lie on the unit circle, right? And in this special case, you very neatly see what the new coordinates become. So let's say you started off at x-axis here, and you rotate it up with an angle theta, and you see that the new coordinates will be cosine theta and sine theta. So rotate the x-axis by a angle theta, and the new coordinates will be cosine theta, sine theta. That you incorporate in the matrix by letting the first column be exactly that. So I show you this example. You take the x-axis, you map it through a matrix, and you want to obtain these two. Well, the matrix that does that for you is the one that has the leftmost column equal to this. Then take the y-axis. I can actually draw that here. Now, here's your y-axis, and now you want to rotate it by an angle theta like that. But now, you will get the cosine by definition here, right? Yeah, this has length 1 by the way. So this is, and then on the y-axis you will get, of course, sine theta, but it will be on the negative side, so you get minus sine theta, right? It means that this is what you get when you rotate the y-axis. As I show here, that's the other column. So rotational unit vector is basically given. You see directly why you have these two columns. Now, any number else this vector would be, it would be the same operation. It's just that the vector would be longer, but it will still rotate through an angle theta, right? So this operation does not change the size of the vector. It doesn't move it from the origin. It just rotates it around in an anti-clockwise manner. And if you want to go in a clockwise manner, you just take the transpose of the same matrix. So it's quite simple. The original matrix, anti-clockwise. The transpose, you go clockwise. So you undo what you did. Now this is in 2 dimensions. Or you can say that this is in the xy plane. If you do that rotation in the xy plane, it basically means that if this is your c-axis, it's the axis you're rotating around. Right? So this is a rotation in 3D, it's a rotation around the c-axis. Let's see if it's streaming. Yeah. Okay, so, but then of course you have to represent it in a 3x3 form because you do it in space. Of course this is again inserted into this 4x4 matrix, right? So this is the 3 times 3 left submatrix of this bigger 4x4. So here you have this R, whatever thing, and then you have 0, 0, 0, 1, and then you have whatever translation will be over there. So you see rotation around the c-axis exactly the same I showed you, except you have the zeros added around here, right? The top one, you do the same except that you do it around the x-axis, so you go from y to c and so on and so forth. And the middle one I showed you here is rotating you in the xc plane, like that blue arrow shows. So these 3 matrices gives you rotations in the different planes in 3D. Right? What if you want a general angle? What do you do? The magic of this is if you want to do this on a general angle, not just in one of the planes, but you want to rotate it through a more general angle. How do you do that?
You need to rotate 2 coordinates.
Yes?
You have to rotate from a vector or line.
Yeah, for example, you can do that, but can from these operations
You combine them one after the other, you chain them.
exactly you multiply them with each other. So whatever angle you want to do in the xy plane, for example, followed by the xz plane, will make you rotate around an skew axis, as you say, and that angle will be just the product of those 2 matrices, whatever angle you choose. And that's the magic of all these things, for all these 4x4 matrices which are together. Any operation we do is just a multiplication of several matrices. I'll get back to that soon, but anyway, these are rotations in 3D, and as you say, in the GLM, you basically first define a 3 vector, which is the axis in space you want to rotate around. So you don't. I mean, in that case, you can just choose any axis you like. For example, in this case, you have x, y, z axis. So in this case, you will rotate around y. If you put that on equal to 1 as well, you would have something that would tilt out, right, between x and y. And then depending on what numbers you set here, you will get different axes you rotate around. Then you input that into this GLM rotate function. So here you put your rotation axis and then the angle you would like to rotate around that axis. Try to play around with that to figure out what axis you get by setting different numbers here. But the basis is on all this are all these three rotation operations line insets. Yeah.
Does the length have to be 1?
No. The length can be anything. The clue is that the vector doesn't it doesn't change its shape. It just rotates, right? So the scaling is another operation, and then we have a translation which moves it around the origin. This basically, if your vector is bound at the origin and has a certain length, it will just change its orientation. Or if you have a square like that, you rotate it through 45 degrees, you keep the shape, right? But you get oriented differently.
Oh, I meant the rotation axis. Does that have to be length of 1? I guess.
Well, I think it is by default. There's no reason why it should be anything else. It's like when you define your coordinate system in space, you would like orthonormal vectors because you only want to define the direction. You don't really care about the length. So then you usually keep the vectors normalized, so it's 1. Right. Oh yeah, you mean if it has to? Oh yeah, that's what you mean. Ah, sorry. No, I don't think it needs to be. I don't think it needs to be. I can get back to you on that, but yeah, I see your point. Because if you have 1 on all of them, yeah, it's not a length 1 vector. So no, I don't think. I think you just set. I can look at that afterwards. Right, but I think you could just. It doesn't really matter because you just want to define the direction around which you rotate. And the number you put in here is just 1. It would be the z-axis, no? Or yeah, and you weighted some of them. No, I don't think it matters. It can have different lengths. It's just that around this axis you will rotate. So I think it could have any length. If I discover that there should be 1, I can get back to you later today or on the lab on Tuesday if you want to do that. But I don't think it matters really the length. It's just a set of numbers telling you the orientation of the vector. Right, so here's a very important point. To move a vector generally, you would like to scale, translate, and rotate your vector, right? All these 3 operations. Now the neat thing is when you have all these 4x4 matrices, your resulting matrix is basically a product of all of them. And once you have that product, that's the one you use to transform your vertices with. So you don't have to do those multiplications again and again and again. But it's very important the order you do things. So you can think about that. You start out with a world reference coordinate system. Then you scale your object to whatever size you want it to be in. Then you rotate it with respect to something to find the orientation you would like. And then you can start to move it around. That's usually the order of things, because then you have control of what you're doing. If you go the other way around, yes, it's a completely legal operation, but you end up somewhere else, right? So for example here, here I have oriented on the upper drawing here, I have oriented this square in the way I want it, and then I can start to move it around and translate. If I do it the other way around, I translate, then of course the origin, in this case you're just rotating around the origin, right? So the origin doesn't move because it's 0. But here I move the origin so it has a number, right? So now I start to throw the whole thing around in space. And here you, for example, if you wanted this to move around the x-axis in your on your screen, in this case you might just throw it out for all you know, or it ends up in a place where you don't want it to be. So the rule is you scale to whatever size you want, then you determine its orientation by rotation, then at the end you move it around in translation, right? And you can remember that as a TRS rule, because when you do this with matrix multiplication, you have to do it the other way around. So you start off with whatever vector you have, then you scale it, then you rotate it, and then you translate it. So it goes sort of like in the opposite direction. And that's why we call it the TRS rule. It's just the order of multiplication seen as you would read text. And this is basically just the same as saying I have a function f of x, and I want to take another function that I take g of f of x, and so on and so forth in a nested way. So remember the TRS rule. Right. So now to the more general space. What I talked about until now is more or less about how you move your local coordinate system with respect to a global one. Right? How you move your object around in the world. But you have more spaces. You have many spaces in OpenGL. I will only talk about 4 of them now because that's what we really need. But these 4 we need to know. So you have the model and object space, which is basically the one you've been using already when you draw triangles, right? So you make whatever model you have and you make it in the local coordinate system. And when you get that one nice and shiny, then you can start to move it around in the global world space, where it's either a part of a larger object, like the car we saw, or it is moving around with respect to other different objects in space, right? Which all have their own local coordinate systems. So this world space is basically the fixed frame for all. Because if you don't have a fixed frame, you know scaling, rotation, and scaling doesn't really mean anything. You have to do it with respect to a global. Yeah, sorry.
Is world space like coordinates in a scene?
Yes. So you can, for example, with the car I showed you, that you could place that in the origin of a global coordinate system. If you have a scene like here, for example, you can have an origin and everything. You know, this room stays the same, so let's say you place the coordinate system here, and then every object would move with respect to that one, right? And they would also have their own coordinate systems. So it's basically the world. That's why they call it world. And then, of course, you have the camera space. You're viewing. You will always have to view in one direction, either through your eyes or your camera, right? Now, here they say represents a fixed absolute coordinate system used. And this is because, I mean, if you're in the world, in the real world, if you want to, you want to look somewhere, you have to move around. You have to move around with the camera or whatever, because the world is staying fixed and you're moving around in it. Now, when you do graphics programming, you can actually fix the camera and then you move the world. Right? So if you want to move to the left in the world, it's the same as moving the world to the right instead. It's a bit mind-boggling, but you can do that because it's nice to have a fixed frame of references. That's usually the camera. So you look in one direction and you move the world around. Yes, so that's basically where the camera is standing. Then you have the clip space, which you may have seen in some of the documents you've been reading until now. And it's basically the position of vertices after you project it into 2D. Right? So now you go from this. As I showed you, you go from this 3-dimensional projective space down to the 2-dimensional projective space. And as you mentioned in the last lecture, it's actually a reduction of rank going on there. So you go from rank 4 to rank 3 when you do that last operation, basically. But this is basically what you do when you go from 3D to 2D. Now it's basically going from 3-dimensional space to 2-dimensional space with this weird points at infinity, basically. But you don't even have to care about them. They're there and they will help you out when the coordinate system is implemented in OpenGL. So that's the last part. You go from world coordinates into screen, in a sense. Right. So before I go further, it's nice to know about the coordinate system in OpenGL. And it's laid out like this. So you have x-axis, horizontal, y-axis, up and down. C is pointing towards you. So if you're sitting on the screen, it's basically pointing towards you in some way or another, right? And you're looking down. Yeah, or I mean, if you change your camera, you may of course see something different. But when you define the coordinate system, this is how it's defined. For example, if this is the coordinate system of your camera, you're looking down the negative c-axis.
So when it looks towards you, it's a plus. When you said C, it looks towards you, right?
Yeah, exactly.
And it's the plus.
Yes, so the plus is towards you. And you can use this right-hand rule here. So you point your thumb to the right, the index finger up, and then the C. These are all positive directions. Positive X, positive Y, positive C. So you can say if this is the XY plane, then this is your positive Z axis, right? And then you're looking in the negative Z direction. Okay? Okay, so we've already seen this. You have your model in the coordinate system, you have the global coordinate system, you have the camera coordinate system, and inside here you have the projection to grip space, as we say, or to your retina or whatever process you want to see this as. Any questions? Okay. So, how do you go from model to world? The first step. Well, we actually already seen that. You scale, rotate, and then translate, basically. So you can start off at the origin and you can move it and orient it in any way you like and place it somewhere in the global space, basically. So I already talked about this, TRS operation. Now, very important is, when you take an object like this, you know, it, for example, consists of 4 vertices, you move the vertices, right? Those are the ones you transform. And if you have many vertices, you know, hundreds of them, it's a bit overkill to compute these matrices, you know, 100 times. So what you do is you figure out how you want to scale, rotate, and translate your image, or your object, I mean, sorry. And then you multiply the matrices together once, and you use the same matrix to transform all the vertices. Then you save a lot. And you have this one matrix that takes care of all those operations. And you will see that you can continue to multiply matrices to map to these other spaces here as well. So now the next one. It's the camera matrix, or the mapping from world to camera here. Right, so how do you do that? Well, yeah, I should probably have this drawing here. As you see, you would like to know how your camera is oriented with respect to the world, right? You want to know what you're pointing at, in what direction that is. You want to know what's up, right? So you don't start to tumble around and you don't know what's up and down. Everything gets weird. So you need a vector pointing up, you need a vector pointing, you know, into the camera, or which is in the opposite direction. The forward vector to the object, whoever it is you want to point this camera at. And then, of course, you need to know the sideways movement. So you need a forward vector, you need an up vector, and you need a sideways vector. Right. So it's basically another 3-dimensional coordinate system. And as with other coordinate systems, you would like them to be at right angles and have a length equal to 1. So how do you design this thing? Well, as I said, your forward vector. So if you have a position P, your camera is located at the position P. Let me take this away. So your camera here at point P. And then you have the world over here, right? And you have some object in it. Let's say, for the sake now, it's the world origin. Now then not the origin, by the way, because then you can just set 0. Let's say it's a point, what did I call it there? T. Thanks. P. And then, of course, in this direction I have a vector. Now I take the difference between these two, I get a vector with a certain length. I divide it by the length, I get a unit vector that points in that direction. So that's your forward vector, right? Then the up vector, as we saw with the OpenGL coordinate system, y is usually up, so you can start out with a y. Now this is not necessarily at right angles to this one yet, but let's say it's the y-axis, right? So you have your forward vector, you have your up vector, preliminary. Now how do we find the sideways vector if we have those two?
Factor product.
Exactly, the cross product, yes. So you take the cross product, and then you get this sideways vector here, S, which is equal to F cross U. Now you have the sideways vector. And that is orthogonal to the other two by by this operation in itself. Now, the last thing you have to do to make sure that the op vector is orthogonal to all the other ones, you just make another cross product with those two, and then they're always right angles. And then you feed all these vectors into a matrix. Column 1, column 2, column 3, and then you try to translate to the origin, which is basically moving it to this point, basically, to the origin. And then you have what is called the lookup matrix, and this is why I use this name, because you don't need to care about the details so much now, but to compute this matrix, to see what you need here, you need to know the position of the camera, P. This one you need to know. You of course need to know the position of the target. This could be the world origin, for example, just to make it simple. You could always point towards the origin of the world. But you could also point other places. So you need to know to calculate these three vectors, you need to know point P, point T, and then the up vector, which is usually the y-axis, right? And again, in
Sorry, P1, P2, P3, are those the coordinates of the P point?
Yes it is. Exactly, yeah, sorry. These are the components of the vector. So this is the component of the sideways vector, this is the components of the modified u vector, and so on, so on. Yes.
But does that mean that if the fourth column means we translate by that?
You translate to the
So
origin.
we translate to the origin.
Yeah. And I call it, it's sometimes called the view matrix, it's sometimes called the lookup matrix, it's sometimes called, but I use the word lookup because that's what it's called in GLM. Right? But you will also see it's named, camera matrix, view matrix, all sorts of names, but they're all the same thing. Camera, view, and lookup matrix are all the same thing. But in code, you always write this GLM lookup. And that is very easy because you have a camera position, when that's defined. You have a camera target over here, T. And you have the up vector. And then you can find this matrix, basically. Then the last step is, of course, to get this down to 2 dimensions. So now we have mapped from here to here using our model matrices, scaling, rotation, translation. We mapped from here to here using the lookup matrix. Now we're going to be inside this camera and we're going to project this down into the sensor, right? And that's basically what you do in this way. There are 2 ways of doing it. You have orthographic one to the left here, which is basically just shining with big light behind your scene and then squashing the whole thing down to 2 dimensions, right? And you have the other one, which is the most natural looking one, is to do this perspective projection. So you project down from P3 to P2. And of course you cannot map back there, so you have a reduction of rank, of course, from this to this point. So there's lots of things you can't read. Of course, if you have many images of the world, you can stitch them together and try to figure out what the original 3D model was. But for our application, it's basically lost for this one because we just want to display it on the screen. And you see the differences. If you do the orthographic one, things will stay the same size. You don't get this weird projective artifact. If you do the perspective one, right, you will see that more remote objects are getting smaller, just like your eyes are working. So the one to the right is very seldom used in graphics programming. It's used if you want to make a blueprint and look at it from different directions. But it looks unnatural, right? It's not how you view the world. And in this case, of course, it's looking exactly how your eyes are doing things. So you sort of recognize this. Now, why would our eyes adapt to the one on the geometry on the left instead of the one to the right there? Any idea?
This is how we see.
Yes.
We need depth to know where.
Yes, we need depth, but there's another. Yes, of course, but there's another thing.
They all meet at a point. Right?
Yes, it all goes down to a very small, because if you want to see a large part of the world, this one, you would need to have your cinema screen size to the retinas, and I don't I wouldn't like to live in windy Norway with this sort of ice. I think you could just blow away like a sail or something. So the neat thing about this is you can take a very big world and project it down into a very small patch, and then sort of get an idea about what's out there in a very wide angle. So mostly in this course we will deal with this perspective projection. Now I won't go into details on how you derive this thing. There are documents online where you can see this in detail. I also appended a document at the end because it's a bit long and daunting task, but this matrix does this for you. Basically. And what it does, and it does it it does this by making a object called a frustum, which is basically, if you look, now the reason, we have to remember that our eyes are of course seen in a more circular way. The screen is like square, right, or like a rectangle. So then the world becomes sort of like a rectangular thing shifted outwards. And the scene you're rendering at any given time, the things you want to be displayed on the screen is what's inside this frustum. And if you see the stepped lines here and the front and the back plane here, it defines a pyramid with the top cut off, basically. So when you do this projection operation, you will define this front plane, back plane, and the top, bottom, and left and right here, basically. And once that's defined, you know what you will be looking at in space. And anything outside this one will not be visible. So when you render the world, you would be interested in knowing where this frustum is, because that's the thing you would like to put on the screen at any given time. You don't want to do a lot of computations and then try to display a lot of things which is not there. It's very important to know where it's located. And that you sort of decide by setting things into this matrix. But instead of setting these bottom, top, right, left things which are scaled, right, as you move along, you can use quantities that doesn't scale. And angle of view, for example, is the same all the time. So the field of view in the vertical direction stays constant, right? Because the angle here is basically the same all the way. And the aspect ratio, the ratio between vertical and horizontal is the same also, right? So if I have this one or I have a rectangle that's just scaled up, is the aspect ratio, it doesn't change. So you specify left, right, top, bottom by viewing angle in the vertical direction and aspect ratio. And then you need to know the distance to the near plane and the far plane. An aspect ratio usually has to do about the pixels on the screen, for example. And then you put this into this matrix. And you can do that in GLM, using GLM library quite simply. So you have your aspect ratio. Here's, I don't know why these numbers were chosen. I should probably have chosen, yeah. Let's say it's 4:3.
What is that?
Basically 4 units there, and it's basically the difference between horizontal and vertical. So let's say you have 4 units here. Oh, sorry, I should draw it here on the camera so people can see. So if this is your screen, then you have 4 here and you have 3 here in this specific example. But this will usually be the number of pixels in each direction, for example. Will define your aspect ratio.
I'm sorry, what, the matrix? What?
Oh yeah, sorry. This matrix.
So yeah, what
Perspective.
is the F? The F over aspect? The first entry of the matrix?
Oh yeah, sorry. Yeah, that's the field of view. The field of view in radians.
Okay.
Sorry, I forgot that one. Yeah. It's this angle here. Vertical angle of field. Yeah.
So what would that number be?
Well, I think that may vary. I think that also depends on. Yeah, that may vary. For example, with a camera, you may have different viewing angles, right? So it depends if you want to see this as through a fisheye lens, or if you want to see your world through, more like your eyes or whatever. So that will depend on, or if you want to just see a little, a little part of the world at once, like through a light spot or whatever. So that's not necessarily fixed. But I think that the aspect ratio is more or less given from what you have on the screen usually. Or it depends. You may have a smaller window that you render this in. So the aspect ratio may also be different. There's no solution to exactly what you said, but usually you don't see more than between maybe 130 degrees is the biggest angle you would choose, for example, and then you can have viewing angles typically of 60 degrees and so on and so forth. Yeah.
Another question. I didn't quite get why you go from world space to camera space instead of just going right straight from world space to clip space.
No, it has to do about you have to point your camera in one direction, right? You have to point it somewhere in space. So if I would like to see this part of the room, I would have to point the camera there, depending on the viewing angle. If I would like to see this part, I would have to point the camera there. Now in graphics program, you actually do the opposite thing, you move the world instead. But it's with respect to that coordinate system. And then the next step is to get this down to 2D. Okay? Yeah. Okay, so yeah, basically to find this matrix, you use this GLM perspective. You set the field of view, vertical field of view here in radians. You put the aspect ratio on the screen, and you put the back and front planes. And they may also vary depending on your application. The point is that when you do this, you define this frustum and how the size of the field of view, the front-back plane, and all this basically determines what you see at any given time when you point the camera in space. So whatever you choose these things to be, which I think is quite free to choose, of course, there's no point in choosing them larger than 180 degrees; it all gets messed up. But you can have varying sizes on this, and depending on the size, really decides how much you see on the room. If I would have just this field of view, I would just see half the room. But with my field of view, I see the whole thing. Right? I don't see what's on the side here, but that's because this frustum is quite big for our vision. Right? Any given camera usually has a much smaller field of view. But anyway, what you render, what you end up with on the screen is what lies inside this thing. And here comes the point about all these 4x4 matrices that we see. What you do in the end when you want to go from your model to the screen is basically matrix multiplication. So you make your model matrix, scale, rotate, translate, you put up your view matrix, you multiply with that, last you multiply with the projection matrix, which is more or less, once you have these two basically identifying numbers, you do most of the work over at the model matrix here. And then basically you're mapping from your model coordinates down to the homogeneous coordinates that you define that you have on your screen. It's basically multiplication of all these matrices.
I'm sorry.
Yeah.
The view matrix, is that the one that we define? Look at?
Yeah, look at, yes. So it's called sometimes camera matrix, sometimes view matrix, sometimes look at matrix. Because in code in GLM they call it look at. So it's a bit confusing that they use all these words, but that's what they do. Sometimes it's also called the I matrix, just to make it even more. But it's all sort of telling you the same thing, right? You look at, you view, your camera eye, basically relating to that orientation. Okay, just see if I'm still. Yeah. All right, so I should probably get going so I get through this. Now, to the point of draw. Don't overdraw is a thing one can remember. So if you look at this scene here in 2D, we have two cameras, camera B and camera A. And for example, in camera B, it would be no point in trying to display all this what's behind you because it really doesn't matter. So you need to know where this frustum is lying, basically, compared to your world. And in the camera A, for example, because of the steep angle between this red block and green block, you will just see this thing. So one should think at any given time what is the point in actually rendering. And another thing is, if you just think about triangles, you only care about the point that's facing towards. Yeah, sorry.
What's overdraw?
It means that you wouldn't like to sort of manipulate and try to put all this out at once because you're just seeing a very little part of the world. So what you want to draw at any given time is basically what you see.
Can you tell it to know if you can't see it, don't draw it?
Yes, I mean that's you can, because you have this fixed camera and then you move your world. You just have to keep track of what is in your field of view at any given time. What is inside this, which is illustrated by this this figure here. If you want to play a little bit around with this exact figure and how what you see and what you draw is basically given in this tutorial here.
Like the homogeneous coordinates one, or the protective
The
spaces?
three matrices.
Oh, there.
Yeah. But you should also look at the other ones there. And, but all of this, I mean, I don't mean you should read all of this because it's a bit overkill, but you will find information about some of the things. The best is probably this Super Bible, which I think we will use as a teaching book next year because I think it's nice to have. But there, if you read page 55 to 89, you get the idea. It's laid out in a very nice and explicit way. If you want more mathematical details, you have all these different things which I talked about. Of course, you don't need to read them all to get through this course, but if you want to know more about these things and understand them to some extent, then...
Can you repeat which one you say you recommend?
Well, the one on top, if you have that book.
Oh, yeah.
But I would actually recommend all of them, depending on the level of detail, but the one on top is actually very nice and simple, right to the point, right? I also think that this tutorial here is okay, but it's very short on things. So you they always talk about how enormously mind-blowing this is, and then you just don't really stick with a lot of answers. So if you want more answers, you have the Wikipedia page just talks about all of these things in more detail, and there you can read as much detail as you like. So that's, if you want to go further, you jump to these pages and you see what they say. And then, you also have some other things here. This tries to explain this projection matrix, which I showed you how it's derived, for example. If you read that, you have a nice explanation there. Yeah.
Could you go back to the previous slide?
Oops.
This one. So what if we had some really complex objects to draw and it took the GPU like, let's say, half a second. So if you turn the camera and it's not drawn yet, you would notice it appearing out of nowhere. Would we have to draw more than the field of view actually sees, so that doesn't happen when we turn the camera?
Well, you have this swapping of buffers, right? So you often draw to a buffer that is not visible at any given time, and then you swap them. And this is to avoid that you get that effect that nothing is, or that something appears out of nowhere. If you look at the code in the labs, for example, you have this GLFW swap window sort of thing to avoid that. But I think you should always try to figure out what comes in the next scene, right? Depending on how things move, and then you sort of have that ready so that when the next you want to show it, you just swap the buffers and then.
How many buffers do we have?
I think it's just swapping between two, but you can also have this triple buffer swapping. Yeah. I don't know if it's supported. I haven't checked that. Anybody knows? Maybe. I think it's 2 buffers at a time. You have a display buffer.
Regularly it's 2, but you could make it 3, but regularly it's just 2.
Yes, I think so. But I think having 3 would be very neat because then you can also save a lot more time and it gets even smoother. Right, so just before we end, I will just very briefly wrap up. So you have model, world, camera, and perspective, basically these 4 worlds. And the good thing is that you just multiply the whole chain together. You start with whatever position you have, you scale, rotate, translate. So here is where you do most of the work. Then you figure out what your U matrix is, depending on where you want to point in space. You multiply that with the rest, and then at the end you have this standard projection matrix, which is defined by aspect ratios and viewing angles and those sort of things. From right to left, so that's important thing. And what is interesting here now is that, and we're going to see on that lab on Tuesday, is that what you need to do, you have a set of vertices, positions that you take in, and all you now need to do is to send all these defined matrices over, just multiply them together in the vertex shader, and then pass them out. Now you have one object that you can do a lot of things with, like I show with this. Just show it again here, in case everybody wasn't here. So you start off with this simple triangle here. This is just translated back and forth. And then you add on more and more triangles that are rotated and scaled with respect to this one, moving like that. And it's just one triangle that you render again and again and again. You use the same model and you just output different scaled and rotated and translated versions of it. If you do that with enough triangles, you get something like that. So it just shows you what you can do with a very, very simple primitive and some, linear algebra, basically. Yeah.
Does it take a lot of memory to run that?
I think this one, if you look at this one, it's when I have 1,000 triangles, my computer starts to...
Yeah, you can see it in the end. It starts to...
When you start to see all the edges of the triangles, this starts to get a bit shaky. So this almost kills my computer. If you want to, yeah.
Would you recommend doing that, or is it just to show what it looks like?
It's just, this is just to show. I think that if you should do this in practice, you will probably do a smarter way, but this is how lab 1 is constructed. You basically have one triangle, you make a struct that describes the triangle with what you start out with is basically this baseline. So just a triangle as a bit, in the previous lab. And then you start to scale and rotate and translate this around and just put one on top of the other and you get this fancy thing. So it's just to show what you can do with simple things. And by the way, to repeat that, you transform the vertices, basically. And then the rest just follows. Okay, so I think we're over time here. Ja, jeg kan prøve å se på det. Jeg har ikke lovet at jeg klarer å skru oss.